Okay, the last speaker of the conference in the day, Sreevani Jarugula, who's at University of Illinois, working with the SPT collaboration. Yeah, you're going to share with us some results on redshift 6.9 dusty galaxies. So take it away.
Thanks, Caitlin. I'm Sreevani Jarugula, a final year PhD student at University of Illinois, Urbana, Champaign, and I'm part of the South Pole Telescope sub-millimeter galaxy collaboration. So in this talk, I'll be presenting our analysis on molecular line observations in two dusty star-forming galaxies at redshift 6.9. Before moving on, I would like to thank all the organizers for giving me this opportunity and everyone who has managed to stay until the very last talk. A little bit of an introduction on this really interesting source, SPT 031158. It's a pair of lensed galaxies at redshift 6.9, which is less than 800 million years after Big Bang. And this is one of the most distant detection of dusty star-forming galaxies in literature. Like I said, these are a pair of gravitationally lensed galaxies labeled as West and East. West is magnified by a factor of about 2.2, and East is barely magnified with a magnification of about 1.3. So in the image, in green is shown the HSD observations, and in red are the ALMA 160 micron observations. So we detect UV emission from East, but we do not have any detected UV emission from West. And the green source that you see on the right side of the plot is actually the emission from the foreground lens. Both the galaxies are extremely luminous with really high star formation rates. And this is actually comparable to luminosity of other high redshift submillimeter galaxies and quasars above redshift 6. And most of this luminosity is coming from star formation, as there is no AGN that is detected in these galaxies. Here are some of the recent observations and some of the published observations on this source. On the top left is the high resolution ALMA 160 micron continuum, and you can see the clumpy nature of both the sources at this high resolution. And the O3 and C plus analysis is presented in Moroni 2018. And from the C plus and O3 ratio, we can see that these two galaxies are physically a little bit different looking at this ratio and also looking at the C plus to LFIR ratio. In addition to these two, in addition to the O3 and C+, we also have unresolved molecular CO observations presented in Standard 2017. And by unresolved, I mean the West and East are not separated. So in this analysis, we present resolved mid-J and high-J CO transitions at a resolution of 0.3 to 0.5 arc seconds, which corresponds to about 1.6 to 2.7 kiloparsecs at this redshift. We also have a detection of a water transition, and this is the most distant detection of water in a star-forming galaxy without an evidence of an AGN. So on the top panel, the background is ALMA continuum emission, and the contours are the moment zero contours of the molecular lines. And the bottom panel shows the spectrum in West, which is shown in blue, and in East, which is shown in green. Okay, so what information are we getting from all these molecular lines? It's really important to understand the molecular content of a galaxy to really know the star formation rates going on in these dusty star-forming galaxies. But molecular hydrogen is really difficult to observe. So the next best option is to observe the carbon monoxide molecule, and the different transitions of CO are tracing different regions of the galaxy. Another good alternate tracer to CO is neutral carbon line, which is not as prone to photodissociation as CO is. And it has been observed that the luminosity of neutral carbon is actually highly correlated with the low JCO transitions. So that makes it a good gas tracer. And water is also a really abundant molecule in the universe, and it has been shown in the literature that there is a tight correlation between the water and infrared luminosity, and this correlation extends over more than 3 orders of magnitude, as shown in the plot on the right. And so because these galaxies are gravitationally lensed, we perform a visibility-based lens model by assuming a source plane structure like a SAZERAC or a Gaussian profile. And here's an example of how the lens modeling looks like. Okay, moving on to the results. So we look at the correlation between the water transition and the far infrared luminosity. And it's been shown in the literature that this transition is a good tracer of far infrared luminosity, which holds true at redshift 6.9 in this source. Because of this relationship, water can be used as a star formation rate calibrator. And when we compare the spectral line energy distribution in 0311 with the other local and high redshift star forming galaxies on the left, and with the local AGN and high redshift quasars on the right, we see that the SLED peaks at the mid JCO transitions as expected of the high redshift submillimeter galaxies, unlike the high redshift quasars, which peak at a higher JCO. And when we look at the ratio of the high J to mid JCO and compare it with the local starburst and AGN and high redshift ULUGs and quasars, we find that the CO 10 to 9 to 6 to 5 ratio is actually comparable to low redshift AGN and high redshift quasars. Although we cannot infer the presence of AGN from this plot, we can say that in addition to photoelectric heating, there are other heating mechanisms, probably something like X-ray heating from AGN, or even mechanical heating from AGN, or stellar activity like stellar winds or supernovae explosions or mergers. Given that we have these multiple CO transitions and also a really good coverage of photometry, we perform a radiative transfer modeling, and we model the dust, CO, and neutral carbon together. And some of the parameters we estimate from this modeling are gas densities, dust and gas mass, temperatures. Here is how the modeling looks like. So the first panel is a single component radiative transfer model, where we assume that the ISM consists of just one component. In the middle, we have a two-component model. So the blue is tracing the cold diffuse component, while the red is showing the warm dense component of the ISM. And in the bottom panel is a turbulence-driven radiative transfer model, which is a more realistic representation of the ISM. And in this model, we are sampling about 50 gas densities from a probability distribution function. And from the modeling in West and East, we can see that our models reproduce our observations pretty well. So from both the observations and modeling, we can estimate properties of these galaxies, such as gas mass and CO luminosity, from which we can calculate the gas mass conversion factor. So one way we get the gas mass is from the radiative transfer modeling, but there are other ways of estimating gas mass. And one of the methods we use is to calculate gas mass from dust mass, which we get from SED fitting and assuming a gas to dust conversion factor. And we can also calculate gas mass from the observed neutral carbon emission line that we observe in 0311. So alpha CO is traditionally, it is assumed to be 0.8 in new lugs and about 4 in main sequence galaxies. However, there is like a lot of discrepancy in the value of alpha CO. It can range anywhere from 0.4 to 6, depending on what assumptions go into your dust estimates and your gas estimates. So on the left, we have alpha CO on the y-axis and far infrared luminosity on the x-axis. And there is a lot of scatter in the alpha CO values in high redshift submillimeter galaxies. And 0311, the alpha CO estimated in 0311 from all the different methods, it lies within that scatter. On the right is this dust temperature on the y-axis, and we see a statistically significant correlation between alpha CO and dust temperature in the SPT SMG sample. And such a correlation has been observed in main sequence galaxies, as discussed in Magnelli 2012. When we can calculate the depletion time as a star formation rate over gas mass. And from this plot on the right, we see that there is a slight evolution of depletion time with redshift up to redshift 3, and such a trend has been observed in main sequence galaxies. But beyond redshift 3 up until redshift 6.9, we do not see any sort of evolution in depletion times. I will leave you with the summary slide. We have more analysis and more observations coming out of this source, so please stay tuned for more. Thanks.
Great, thank you so much, Sreevani. We'll wait for a few questions to come on Slack.
Okay, here's one about, since these are high redshift galaxies, the person is wondering if it's necessary to consider cosmic ray ionization in your analysis, or maybe you can just include that as a mechanical heating.
Yeah, that's a really good question. It's important to consider all these effects at high redshifts. So the radiative transfer modeling code that we use includes a kinetic temperature to dust temperature scaling, and it's a free parameter. So that could vary based on any sort of mechanical heating or cosmic ray heating. That parameter is free to vary. So we are considering all these effects in the radiative transfer modeling, but we just don't separate them into cosmic rays or mechanical heating.
So while we wait for other questions, I was going to ask one, and perhaps you said this, and I'm sorry. So obviously the SPT sample in general has a remarkable suite of observations to constrain molecular gas, arguably better than any other sample we have at high redshift. And you have all of these tracers. You have dipping into lower J. Well, and you have the C1 and you have the dust continuum. So in your constraints on alpha CO, I imagine you kind of take all of that information into account, and dynamical constraints too. Was that alpha CO that you measured just for SPT 0311, or was that aggregate for this whole sample of SPT sources, or are they similar? Can you comment on that?
Right. So one problem with alpha CO is that in literature, like everyone uses different assumptions, right?
Yes.
Calculating alpha CO. A few of them get it from dust masses. Like some of them assume a gas to dust mass ratio of 100 or above 100. Depends on the metallicity or dynamical mass, or even like scaling relations, right? If going from CO3 to 2, say 1 to 0 or something. So to avoid all that, what we did is we recalculated everything using, we recalculated the dust masses, so refit the SEDs assuming the same beta value, and using a gas to dust mass ratio of 100, we calculate the gas mass for all the sources on this plot, including the low redshift and the high redshift sample, just to get them on a same scale when we are comparing.
Mm-hmm. Mm-hmm. Yeah. Cool. Thank you. Okay, we have a question. May I ask the temperature of the cluster where you observed? Not entirely
So,
certain what cluster, but
well, the SPT sample in general has a higher dust temperature because it has higher specific star formation rate. So these are mostly like biased towards higher dust temperatures.
Yeah, I guess we can see on this slide here the range of dust temperatures probed, with the gray points being the SPT sample.
Yep.
Great. Well, I would say any other questions for Sreevani can be dumped in the Slack, and you can all have a great conversation about SPT 0311 and all of the dusty sources from this session.